Welcome to this presentation. I am Dario Santonocito, a postdoc researcher from the University of Messina, and I will present you the work entitled Fatigue Damage Assessment of Welded High-Density Polyethylene Details Evaluating Their Energy Release. The aim of this work regards the investigation of the fatigue properties of welded high-density polyethylene specimens adopting full-feed techniques such as infrared thermography. The mechanical properties of the material were evaluated and the temperature trend of the specimen surface was monitored during static tensile and fatigue tests applying the thermographic method and the static thermographic method. In particular, the static thermographic method is proposed as a rapid test procedure able to correlate the temperature trend to the fatigue properties of the material during static tensile tests, adopting a very limited number of specimens. Thermography has been used as an aid for assessing the fatigue properties of several kinds of materials. As observed by La Rosa and Risitano, if we cyclically test a material with a stress above its fatigue limit, the temperature evolution of the specimens monitored with an infrared camera is characterized by three phases. An initial rapid increment in the first phase, then it reaches a stabilization temperature, and finally, in the third phase, a very high further temperature increment until failure. Generally, the higher the applied stress, the higher the stabilization temperature, but on the other hand, the subtended area of the temperature number of cycle curve could be assumed constant and related to an energy parameter phi. If we report the stabilization temperature versus the applied stress, the fatigue limit of the material could be defined as the intersection with the stress axis. In addition, if we stress in a stepped way the material and we evaluate the energy parameter and the different stabilization temperature, it is possible to obtain the number of cycles at which the material will be broken if we cyclically test with that stress, hence obtaining the SN curve. The static thermographic method has been developed during the last 10 years. The first paper by Risitano and Risitano was presented in 2009. In 2013, Risitano and Risitano proposed the static thermographic method as a rapid procedure to derive the fatigue limit from a tensile test. During static tests of common engineering materials, the specimen's temperature is characterized by three phases. An initial approximately linear decrease due to the thermoelastic effect following Lord Kelvin's law. Then, in the second phase, the temperature deviates from linearity until a minimum, and finally it experiences a very high further increment until the failure. If it is possible to estimate the stress at which the temperature trend deviates from linearity, that stress could be related to a critical macro stress which is able to produce in the material irreversible microplasticity. This critical stress is the same stress that, if cyclically applied to the material, will increase the microplastic area up to produce microcracks, hence fatigue failure. High-density polyethylene is a material widely adopted in pipeline for gas and water distribution. Sometimes it is necessary to weld different sections of the pipeline, for example fittings. According to the Italian national standard, the welding process consists of two phases. At first, the two sides of the pipelines are heated up to fusion, adopting a thermoelement. Then, the two parts are joined applying a prescribed pressure for a certain time. The tested specimens are retrieved directly from pipe, according to the geometry of the ISO standard for plastic material testing. The weld bed was removed by milling the surfaces. Three kinds of tests were performed. Static tensile tests on 3 specimens adopting a crossed speed of 5 mm per minute. Stepwise fatigue tests applying the thermographic method on 2 specimens with stress level from 10 up to 17 MPa with a stress ratio of 0.2 and test frequency of 1 Hz. Constant amplitude fatigue tests in order to obtain the SN curve of the material on 9 specimens with the same stress ratio and frequency of the stepwise test. During static and stepwise tests, the specimen's temperature was monitored with an infrared camera. During static tensile tests, the evolution of the specimen's surface temperature has been evaluated by means of an infrared camera. The applied stress is reported versus the specimen's surface temperature variation, estimated as the difference between the instantaneous temperature and the initial temperature of the surface recorded at time 0. The temperature data has been filtered with the air loss filter with a data span of 10% in order to reduce the outliers and highlight the thermoelastic trend. In the initial part of the temperature time curve, it is possible to clearly distinguish the linear trend of the temperature, then it deviates from the linearity, reaching a plateau region. It is possible to draw two linear regression lines, the former for the first linear phase and the latter for the second phase, not taking into account the temperature values near the slope change. Solving the system of equations, it is possible to determine the intersection point of the two straight lines. The corresponding value of the applied stress could be related to the microscopic stress that introduces the first microprecipitation phenomena in the material. All the tested specimens failed in a section far away from the welded area. The other two static tensile tests exhibit the same temperature behavior. The value of the limit stress assessed by the static thermographic method is equal to 13.9 plus minus 0.1 megapascal. Fatigue tests with a stepwise increase of the applied stress level have been performed on two specimens with a stress ratio of 0.2 and 1 Hz of frequency. During the test, the superficial temperature has been monitored with the infrared camera. For each stress level, it is possible to observe and estimate a stabilization temperature. In particular, for stress levels below 14 MPa, we observe none to very small temperature increment compared to the first cycle temperature. As the applied stress is greater than 14 MPa, it is possible to observe higher stabilization temperature. For the last stress level, no stabilization has been reached and the temperature increases until the specimen failure. If we report the different stabilization temperature versus the applied stress level, it is possible to observe two linear trends with different slope. The first linear trend is typical of stress level below the fatigue limit of the material and can be addressed to noise in the temperature signal or material damping, while the second is characteristic of energy release due to fatigue damage phenomena. By the intersection of the two linear trends, it is possible to assess in a very rapid way, even with one specimen, the fatigue limit of the material. A series of fatigue tests has been carried out on 9 specimens with constant stress amplitude from 13 up to 19 MPa, and the same stress ratio and frequency of the stepwise fatigue test. The test results are reported in a SN plot adopting a number of cycles for an out of 1 million, with a scatter band for a probability of survival of 90 and 10%. The fatigue limit estimated with a probability of survival of 50% is equal to 13.5 MPa. On the other hand, the limit stress estimated by the static thermographic method with only 3 specimens is equal to 13.9 MPa, while the fatigue limit estimated with the thermographic method on 2 specimens is equal to 14 MPa. These values are in very good agreement with the fatigue limit assessed by traditional fatigue tests, showing how it is possible to estimate this value in very short amount of time. In conclusion, in this work, the energy released during static tensile and fatigue tests on welded high-density polyethylene specimens has been evaluated. The infrared camera allowed the application of the static thermographic method and of the thermographic method, monitoring the specimen's surface temperature. By the static thermographic method, the average value of the limit stress has been evaluated as the stress level at which the temperature deviates from its linear trend, obtaining a value of 13.9 MPa. By the thermographic method, the fatigue limit has been evaluated as the first stress level for which higher stabilization temperatures are observed. Its value is equal to 14 MPa. This value has been compared with traditional fatigue tests, showing a good agreement with the fatigue limit of the material. Energy methods, and in particular the static thermographic method, could be adopted as a fast test procedure able to predict the fatigue properties of the materials from a conventional static test in a very short amount of time, 5 minutes per test, and with a limited number of specimens, even free specimens. Thank you for your kind attention.